I'm not the only presenter today, actually. We have Dr. Arash Mahdavi, who is our leading researcher on link of AI and simulations. So Arash will be helping me with AI terminology. He's making sure I don't say something really, really wrong. All right, and Anatoly is not here today. I'll duplicate what Chris said a little bit, just to put us in the context of this symposium, and we'll start with the things that we don't do. So what we don't do is control systems like hardcore physical modeling, like hydrodynamics, aerodynamics, sensors, actuators. So we leave that stuff to softwares like MATLAB, Simulink. So to put it short, what we don't do is edge and control, right? So, but we do everything above that. Systems that are being modeled and simulated with AnyLogic include things like factory floor operation, pedestrian flows, road traffic modeling, like multimodal terminals, mining facilities. Then slightly larger scale things like supply chains and models that are where space is geographical space, and all the way up to strategic level models where objects you're modeling are, for example, like competing companies, product portfolio, where time horizons of models can be like years or decades. So in this space, you can pretty much assume that 40% of the models created today are created with AnyLogic. There's no kind of formal data or formal research on mind share or market share, but here are some numbers that will tell you that our presence and footprint in this market is only growing over the last several years. Now, if you look at the industries that are using AnyLogic, we are a general purpose tool. We do have some libraries supporting particular verticals, but we're really used by across many industries. And you can see from banks, insurance companies, all the way to mining, from railroads to military, etc. Now, although our main topic today is how AI links to dynamic simulation, I'll do a little bit of intro on what is modeling and simulation, and we'll also do a case study on digital twin. I'll show a digital twin of gas turbine fleet created with AnyLogic. All right, so this is my favorite slide about modeling. I'm showing it. It's old. I'm showing it every time. So if anybody in this room has seen it, well, I'm sorry for you guys. We'll go through through all this stuff again. So you have the real world, and there is a problem in the real world, and you look for a solution. And it may happen that experimenting or finding a solution in the real world is not possible. It may be too expensive, it may be too dangerous, or the objects might not yet exist. So now what you do, you go up from the real world to the world of models. So you build a model of your system, and this process is informal, is kind of art, and this is a process of abstraction. So you throw away things that you think are not important, you leave those things that you think are important for solving that problem. Now then, there, in the world of models, you do your experiments, you do your calculations, optimizations, you find a solution, and you map it back to the world of models. So modeling is actually this journey through the risk-free space. Now, there are different types of models out there. There are like mental models that we have in our head and use all the time and every day. There can be physical models, like, for example, a toy railroad is a model of real railroad. There are analytical models, and likely there are tons of Excel-based models out there. But our topic is obviously dynamic simulation models. So what is dynamic simulation? And this is exactly what AnyLogic does. Dynamic simulation allows you to build, let's say, a trajectory of how the system state changes over time. So dynamic simulation tools allow you to build a possible future of your system and show you how that future is reached and how it develops. Now, in case the model is stochastic, there can be not one but multiple trajectories like this, a tree of those. Now, the great thing about dynamic simulation is because we explicitly go through all these states, a sequence of states in time, that everything which is obviously not beyond our level of abstraction is accessible and measurable. So dynamic simulation is not a black box like, for example, a Excel spreadsheet could be, or some AI could be, right? Because you always know why something happened, right? Now, the software that we develop is built well and always works. Therefore, I can afford doing some live demo. So this is AnyLogic Cloud, a public online collection of simulation models contributed by the community. And I'll go to, let's say, transportation and logistics, and choose this distribution center model. You can do multiple things here. For example, I can run animation. So right now, the actual model starts somewhere on Amazon Cloud, and animation is going to be delivered to here. So obviously, this is 3D animation. It's interactive, and you can go to 2D. And this is not video. So what I can do, I, for example, can change parameters like can change resource capacities. I can look at the statistics. I can speed it up, etc. And here, obviously, some primitive statistic like order processing time, utilization of resources at the facility, etc. So this is how animation of a simulation model looks like. And you can also do animation-less experiments where you only have inputs and outputs like this. And like you change the input, you can run it in the background. It will execute much faster, and then your outputs are here. Okay. So this is it with a typical demo, and let's go on. Digital twins. So we all know that this word is very much abused these days because people tend to call any digital representation of any object a digital twin, which to my mind is not correct. So I'll try to explain what we mean when we say digital twin. So you have an object, existing operational object that lives its life in the real world. Now, you have a simulation model of the object sitting there, and maybe most of the time doing nothing. Now, periodically, what you do, you take a snapshot of the real object state, and you feed it to the simulation model, and it synchronizes. It's deeply parameterized, and it synchronizes its state with the current state of the object. And then you do your simulation, maybe one, maybe number, maybe do what ifs, having some virtual time horizon in mind, right? Now, when we finish our analysis and forecasting, we send some suggestions to the real world, and then maybe some actions are taken. Now, that is happening not once, but that happens periodically. Now, what is the time between it? It can be anything. It can be, for example, an hour. It can be a minute. I'm not talking about like real times, like milliseconds or microseconds. All that also is possible. It all depends on performance of your simulation and connectivity. Or it can be like imagine this is a supply chain, right? And I can run this like every month or every year. Now, therefore, there are certain requirements to a simulation tool that does this, and this is obviously data connectivity. This is deep. The model should allow for very deep parameterization, so we should be able to set up initial states of all objects so they mirror the current states of the real objects, right? And obviously, simulation performance might matter. All right, so just a case study. That project was performed by our partner DSE Consulting, and the client was Siemens. And you will much better understand terminology here because it's about gas turbines. But the important thing here that the system that was being modeled was not a single asset. Was a fleet of gas turbines that was out there operating at Siemens clients, right? So the story behind it is Siemens acquired a new type, certain type of gas turbine from Rolls-Royce and wanted to improve their maintenance, operation maintenance and overhaul and repair. And instead of using Excel-based, let's say, forecasting tools, they decided to use a simulation-based digital twin. So they were looking at certain KPIs, and they were looking at things like, okay, where to invest best to the engines themselves, to supply chain of spare parts, etc. Now, the next few slides are just videos showing how that digital twin actually looks like. It's an application. Oh, no, yeah. Video will be next slide. This is the scope of the model. The scope is really big. It included not only the assets, but also things like connected supply chain, operation and processes within the maintenance facilities, even like staffing, shifts, all that sort of stuff. So, and now we go to the video. So this is kind of the first screen. Here is where the snapshot is actually loaded, and this is a snapshot of the turbine fleet, right? And then you define the time horizon of the simulation. And then this next short video is shows different screens with different types of KPIs. I will not really do any comments on that. It's probably more kind of straightforward and obvious to you guys because you're in the same type of business. So there's a map, the current states of the engines, and some other charts like shop visits, etc. And finally, there are some other more sophisticated experiments and what-ifs, like Monte Carlo experiments, etc. So it looks like a typical BI with lots of charts, lots of graphs, and some options that you can explore. But underneath that user interface, there is a simulation model built in, with AnyLogic, and that digital twin is already in use by Siemens. Right. And now we're moving to our main topic, which is artificial intelligence and simulation. Now, as you all know, these days people are afraid not to talk about artificial intelligence, right? We were different. We were resistant until the very end because we wanted to stay like hardcore simulation guys. But what happened is that AI developers started approaching us because they felt the need in simulation technology to expand the range of AI applications. So, what is currently happening is that AI has been so successful in doing things like playing chess or playing Go. So AI developers thought, okay, if learning agent that we can train can control can control things like that, why can't it control a manufacturing side? Why can't it control a supply chain, right? So they're expanding from here to here. But the problem is that they desperately need a training environment for their agents. And dynamic simulation naturally provides such type of training environment. Actually, there's no, if you want to train AI to control a warehouse, there's no other way you can go. You need a valid, accurate, and fast model of warehouse to train your AI before it can be deployed to control the real thing, right? Some AI definitions. So anything that can behave like a human is AI. Now, anything that can learn without being explicitly programmed is what's called machine learning. And then the most exciting thing is deep learning. These are actually specifically neural networks that can learn from unstructured data. And obviously, we will concentrate on this stuff later on. Machine learning paradigms is another kind of educational slide. So there's so-called supervised learning. For example, I want to create a spam filter. I have tons of emails, and I can explicitly label them, saying, okay, this is spam, this is spam, this is valid, a real email, this is spam again. And so I feed to my learning agents pairs of this is input and this is known output for that input. And AI learns from that. This is what's called supervised learning. Then there is unsupervised learning, where I just feed unlabeled data. And then a typical task for AI would be to uncover some hidden structures there and do things like, for example, clustering. And then there's reinforcement learning, and this is actually where, as you will see, the simulation will play the biggest role. There's no data, and there AI is learning by trial and error, by interacting with certain type of environment. So what happens is that learning agent observes the state of the environment, takes some actions, and depending on the quality of the action, it is rewarded or punished. Now, that was said 2 or 3 years ago by Lyle Wallace, who was, by the way, one of the early adopters of AnyLogic. He's now director of one of the analytics director of PwC. So his vision was that simulation will be a key part of AI technology, and let's see why. So how simulation modeling, and again we're talking about dynamic simulation, can be useful for AI. First, AI developers suffer from lack of data. And what simulation can do, simulation can generate synthetic data that you don't have from the real object. And you may not have that data from the real object for different reasons. For example, you haven't recorded that data, right? Next reason, something that you would like AI to learn from have never happened to the real object. Or the real object might not exist yet, right? And then what do? You create a simulation model of the real object, right? And you just basically run many scenarios and record some histories, and then feed those histories to the artificial intelligence to learn from. Next thing is, and this is our kind of main setup. Learning environment can be provided by a simulation model. So let's say this thing here is a model of the factory floor and simulation model, and this guy tries to manage the factory floor. So it observes the state, makes some actions, etc. And finally, if you already have trained your AI, and again, in this case, AI is meant to replace somebody who manages something. So we're not looking for AI as like image recognition, or we're looking for AI as a behavior, as a controller, if you will. So what you can do, you can put AI, use AI as a part of the simulation model and actually run some test scenarios and see how well this guy will control the facility. Now, out of these three, the most money is actually invested into here, into that type of machine learning, and people treat that as kind of most exciting type of link of simulation and AI. All right, now very simple example, and the goal is to explain in a very detailed way how we can train artificial intelligence with the help of a simulation model. So, traffic light control. You have a very simple intersection like this. No turns are allowed, and we have a traffic light that controls this intersection. Now, we have also car arrival rate data. As you can see, like east-west is pretty constant, but north-south has a very explicit rush hour. Right. The goal is minimize the time and system for a car and on this intersection. And what we can change traffic light phases. And AI will be trained to control the traffic light, okay? Now, simulation model is easy. We draw a layout. We create the process flow. Basically, these are 4 sources of cars from each direction. We'll link it to the layout. We provide the arrival rate data, and we set up the traffic light. This is it. So we can run the model already. And this is obviously video from a simulation model, and you will see that these cars are going through that intersection. Again, remember that if we simulate something, we can measure anything at any time. What do we provide to our learning agent as a state of this system? The state is really complex because the state includes like every car location, car velocity, acceleration, this sort of stuff. Also, the state changes over time. It changes all the time. So how often do we provide these observations to our learning agent? So in this case, decision was made, okay, we will simplify the state by dividing this intersection into 9 zones and simply calculating like time and system for all cars in each zone. Plus, so this, we will have 9 numeric values. Plus, we will have the current traffic light phase. This is going to be our state, like 10 numbers that we will feed to the learning agent. And we will do that every 10 simulated seconds. Now, these decisions are purely based on intuition and cannot be formalized, right? So you need to have some experience to do that. All right. For the AI, we used this network. It's I know is it considered, Arash, to be a simple or a simple network, right? Yeah. So it has 4 layers, obviously input and output layer, and then 2 hidden layers, 300 nodes each. And obviously, as we do have 10 values as inputs, there are 10 neurons here and 2 output neurons for two possible actions. Okay, there's a simulation model. Observation as we constructed goes here. AI suggests to change phase of the traffic light or not to change. Easy. And then compare it on whether situation at this intersection improved or not. We either reward or punish the neural network by providing this as a reward. And the value is from -1, which is you did bad, to 1, which is you did great. Okay. Learning cycle, and this is the kind of the main setup of training AI with the help of simulation is this. So we have this simulated time. At some point in time, you take observation, provide it to the neural network, receive action, change something in the model, proceed further. Depending on whether that was good or not, we provide feedback. The neural network learns and changes itself, then takes next action and next action, etc. And we do multiple runs. So for this particular model, we did 100 simulation runs, which are also called episodes. Is that an AI term, episode, right? So 100 episodes like that, each having over almost 3,000 learning cycles. And this is obviously learning cycle. We ran that for 30 minutes, which is a very small time for learning in AI world. And let's see the results. So you will see 2 videos right now. So here on the left, you will see the simulation of that intersection with some constant values for phases received by applying a traditional optimizer. So there on the left, nothing will, in terms of traffic light, nothing will change over time. On the right, you will see adaptive policy implemented by trained AI. Okay. So where to look at? This is mean time in system. This is our main KPI we're trying to compare. Again, in non-AI stuff, we're not yet at the rush hour, but we see that AI is already behaving better. And now the rush hour begins, and you will see that this purple line is overall time in system. Of course, it increases because of the rush hour, but it does not increase that much as here. So even in this simple example, AI was able to beat some constant, optimized constant values. Now, of course, this is a very simplistic example, one thing. Second thing, I am able, without any artificial intelligence, to think a little bit and to invent some heuristics that will be even better than the trained AI. But of course, that was created just for demo purposes. But imagine a much more complex system where, for example, have several intersections that are interconnected and obviously interdependent. Then AI will start showing its superiority over any heuristics or over any kind of fixed algorithms. These are some architectures. I won't go through that. For training that AI, we simply imported the SkyMind libraries for deep learning into AnyLogic, but these are option 2, option 3 are probably more valuable architectures for training AIs. Okay. 12 minutes, so I think I should be all right. Very simple demo of AI used in industry. That project was performed by Italian company Engineering, which is also our partner, and they used AnyLogic. So this is about, it's a kind of production scheduling. So you have a facility, and this is a facility where they manufacture ferromagnetic cores. And these guys are really heavy, so they probably tens of tons. And you need to move them around this facility, and there can be bottlenecks because to move something, this guy to here, you probably have to clear that spot, which is currently taken by another core. And the problem is that every core is custom built, so there's no fixed process for which we can obviously plan in advance. So the trajectory of each core is unique. So currently, this floor is managed by actually an experienced human, and the engineering company decided to use not even heuristics, but decided to go to AI. So what they did, they trained an ensemble of algorithms using simulation model for doing primitive like sub-jobs. For example, this video shows that the core has to be moved to this position, and then AI manages that movement, right? And then they created a number of neural networks that together manage the whole factory floor. And these are some details on the reward function, because that was all deep reinforcement learning that they did. And this project is currently being actually implemented at the facility. Okay. Conclusion. Challenges. There are many. First of all, simulation, especially dynamic simulation models, are comparatively slow to execute. Even if the, let's say, a simulation cycle takes 1 second, this already can be too long to train neural network that might need, I know, millions and millions or billions of cycles to learn. So that is obviously a challenge. Of course, the performance of simulation depends on the level of details, on the level of abstraction that you use, but still. Now, the good thing is that there are technologies of parallel learning, right? So a same neural network can learn in parallel from multiple simulations being executed. And the cloud technologies obviously help to scale that up, right? So that problem exists, but there are ways to improve that. Next thing, of course, the model only does what the modeler put into it, right? So if you have a wrong model, then AI trained with the help of this model will also work incorrectly. And therefore, and by the way, the AI developers know not a lot about simulations. So joint experience and collaboration is needed between AI developers and simulation developers. Okay, modeling is art, but AI is even more art than modeling. There are many informal steps there. It cannot be called science or technology. It still is art, right? How do you choose the structure of your neural network, right? How many layers? How do you put together observation, reward function, all this stuff. There are advances in AI technologies, and like companies like SkyMind, with a framework called PathMind, and Bonsai has recently been acquired by Microsoft, are trying to simplify that by providing environments where you don't need to make that many decisions based on your intuition. Finally, there's kind of it's about habit. AI developers are very used to open source software, or they're used to writing everything from scratch. Oh, I'll write a learning environment in Python from scratch. That is probably okay if your neural network is learning to play chess, because I can recreate the chess rules in probably one day, right, or less. But if my AI is to control, I don't know, a supply chain, it's not possible to create a meaningful model of a supply chain in Python in any reasonable time frame. So the only environments where you can really develop such models are all proprietary simulation software tools. Okay, and what I can say that AI at the moment is not sciences like alchemy, right? So people try things, and they might work or might not work. So it's a kind of blind search, right? But the good news is this: in this world, simulation looks more like technology, because there we know that if we do this, this is going to be the result. And if something happens, we can always understand and explain why. All right, so our partners, so we're partnering with leading AI companies, SkyMind, Element AI, Microsoft. Strategic partner is PricewaterhouseCoopers, and industrial partner is McDonald's. And you can see on this slide what these guys are doing and where what is our collaboration about. Useful resources: you can take a picture of this slide and access some webinars, materials, blog posts, etc. And 4 minutes left, so ready for questions.